Hello friends, in this video we are going to see rotation, vorticity and vortex flow. Let's start with the rotation. So rotation already we have seen in the chapter kinematics. In the chapter kinematics, we have seen the definition of rotation. So if the fluid particles while flowing along the streamlines also rotate about their own axis is called rotational flow. And the example I have given, that is, the earth rotates on its own axis while revolving around the sun. So you know that earth also revolves around the sun, and at the same time it also rotates on its own axis. That can be also a good example of rotational flow. So here with respect to fluid particle, I can say the movement of the fluid element in such a way that both of its axes, that is horizontal as well as vertical, should rotate in the same direction. So this is the second definition of rotation. The first one is if the fluid particles while flowing along the streamlines also rotate about their own axis, that is called rotational flow, that we have seen in kinematics. Some more definition, some more details about the rotation. If the fluid elements in such a way are moving in such a way that both of its axes, horizontal as well as vertical, should rotate in the same direction. Same direction means either clockwise or anti-clockwise. So I'm just trying to explain with the help of the diagram. Look at this. So this is the fluid particle I have drawn, and let us see, this is the y-axis and this is the x-axis, correct? So x and y-axis have been drawn for the fluid element. So this is y dash, x dash. So here, as per this definition, the movement of the fluid element in such a way that both of its axes, horizontal as well as vertical, that is x and y, should rotate in the same direction. Same direction means either clockwise or anti-clockwise. So suppose if x is moving in the anti-clockwise direction, then y also should move in the anti-clockwise direction. Y also should move in the anti-clockwise direction. That means the angle between the two axes must be maintained equal to 90 degree. Correct? This is one case. Second case is that if the axis moving in the clockwise direction, the y should also move in the clockwise direction. Correct? So the angle between them will be maintained. So if both the axes, whether x and y axis, are moving in the same direction, either clockwise or anti-clockwise, both can be called as rotation. This is a good example of rotation. But there are cases where you can see that x and y axis are not moving in the same direction. That can be called as a case of deformation. Look at this. And is equal to the half of dou v by dou x, dou e by dou y for a 2D element in xy plane. So when you talk about the xy plane, we have already discussed that is omega z. That is rotation about the z axis and xy plane. So how to write half into dou by dou x minus dou by dou y. Y component will write here and x component will write here. So this is the formula for finding the rotation about the z axis, or you can say xy plane. xy plane. The same it is mentioned in the definition. Okay. Now you can see here irrotational flow. And suppose if the two axes are not moving in the same direction, one is moving in clockwise, another is moving in anti-clockwise direction, then that is called as irrotational flow, and that is called as deformation. So deformed fluid particle you can see here. So so normally our axis is your vertical axis. You can see I'm trying to draw the axis, correct? So vertical axis. Now with this red color I'm trying to draw the new axis. So this will be your new axis and this will be your new axis, correct? So this is the intersection point. So now you can see here, so this red color line, this is moving in which direction? This is moving in the anti-clockwise direction, correct? This is your x-axis. What about the y-axis? Your y-axis is moving, the new axis is moved in the clockwise direction, correct? So this is the case, good example here, where you can see the x and y are not moving in the same direction. So this is not called the case of rotation, it is called deformation. So that is what is written as deformed fluid particle. Okay, and this was the original fluid particle. And here angles have been measured here, beta and alpha greater than 0, alpha greater than 0. Positive angles are defined toward the center of the fluid particle. If the deformation is toward the center of the fluid particle, then it is greater than 0. Both alpha, beta are greater than 0 and equal. Almost you can see the angles are equal. Now look at the deformed particle in the case when you are having the rotational flow. So original fluid particle is here, but what you can see, the good part is that both the x-axis and y-axis are moving in the same direction here, right? Both the x-axis, if you take this x-axis and y-axis, both the axes are moving in the same direction, either clockwise or anti-clockwise. The angle should be maintained same, but here you can see the angle is changed here. Angle is changed here. So this is called as rotational flow when the both the axis, x-axis as well as y-axis, should rotate in the same direction. That is called as rotation. Okay. Now we'll go to the next case, vorticity. So vorticity is also a property of the fluid. It is defined as the value twice of the rotation and is given as zeta is equal to twice omega. So zeta is equal to twice of omega. So this is the equation. So valid for finding the value of vorticity, and it is 2 times of the omega. So omega, you know, omega is generally, let us say if you're writing omega z, it is writing half always, right? Half x minus y. So v and u. So when you take the 2 times, double the intensity of the omega z, that is called as vorticity of the fluid flow. It is a property of the fluid. Next one is vortex flow. It is defined as the flow of a fluid along a curved path, or flow of rotating mass of fluid. Flow of rotating mass of fluid. Note, vorticity is a property of the fluid related to the local angular rotation defined as the curl of flow. So del cross v vector. Curl means del cross v vector. So del cross v vector equal to 0. So if it is coming as 0, it is called as irrotational flow. That we have seen already in the kinematics. Okay, once again I'll repeat. So vortex flow, it is defined as the flow of a fluid along a curved path or flow of rotating mass of fluid. Both definitions. So look at this. I'm trying to give the example of vortex flow. So this is the flow of the fluid along the curved path, or not necessarily it should be a complete circle. Even the half part of the circle can be also called as vortex flow, curved path, or flow of full rotation of the fluid. Correct? Full rotation of the fluid. So these are the direction of the streamlines. So when you talk about the vortex flow, it is defined as the flow of a fluid along a curved path, not necessarily a complete circle, or flow of rotating mass of fluid. And here there's a difference between the vorticity and vortex. It is given very nicely. Vorticity is a property of the fluid related to local angular rotation. Angular rotation means omega x, omega y, omega z. They are talking about. Okay. Defined as the curl of the flow, velocity field, while vortex is a whirlwind, whirlpool, or similarly moving matter. Matter means mass here, in the form of a spiral or column. Next one is your vortex flow. Next, we're going to see what is the difference between vortex flow, that is free vortex, and forced vortex flow. Okay, so vortex flow definition we have seen. When no external torque is required to rotate the fluid mass. When you talk about the torque, external torque or internal torque, first of all, you know that whenever you want to move a body, you need to apply force. So if you apply force in the x direction, you will get the movement in the x direction. But when you want to rotate a body, you want to give angular displacement, you have to apply torque. So first of all, torque is definitely required for any kind of vortex flow, whether it is a free vortex or forced vortex flow. But there are 2 types of torque as mentioned here. With that only we are differentiating what is free vortex and forced vortex. When no external torque is required to rotate the fluid mass. So what do you mean by external and internal torque? When the torque or any kind of force is applied by the nature, I mean when natural forces are involved, then we say that it is internal torque. External torque means we are applying. So when no external torque is required, then it's called free vortex flow. And here we are going to see all natural words like river, then tornadoes, tsunami, all this type of word. So natural words will come into picture. When no external torque is required to rotate the fluid mass, that is called free vortex flow. And when you come about vortex flow, force vortex, external torque is required here to rotate the fluid mass. External torque means we have to supply the torque or power externally. Example, flow of fluid inside the impeller of a centrifugal pump. So you know the centrifugal pump, or it is a washing machine or any motor, we need to supply electrical power externally. So when we have to supply the electrical power externally, that is called force vortex flow. Even if you want to rotate the water kept in a bucket with your hand, that means you are applying the work. So that is called as force vortex flow. When the vortex is created by the natural forces, that is called as free vortex flow. Okay, equation involved in the vortex flow is your v into r equal to constant. V into r equal to constant. So we are going to see v into r into constant means we are going to see in the next page how this equation is valid, where v is the velocity of the fluid particle and r is the radius of the particle from the axis of rotation. When you talk about the force vortex flow, here we are talking about the some devices or some. Let us take the example of centrifugal pump. You know the wattage, it's all electrical device. Wattage is constant. So when the wattage is constant, what happens? It will deliver exact amount of RPM for a fixed voltage. For a constant voltage, it will deliver the exact amount of RPM. So omega will be constant. When omega is constant, I can write V by R equal to constant. So this is the valid equation for your force vortex flow. Omega equal to V by R equal to constant. Correct? But for this, your free vortex flow, the valid equation is your V into R equal to constant. Whereas I can say here, the equation valid is V by R equal to constant. That is omega is constant. Okay, so V equal to R omega we can write. So what is V? V is the angular velocity of the fluid particle. R is the radius of the particle from the axis of rotation. Omega is angular velocity, radian per second, and omega equal to constant, that is V by R. So when omega is constant, your RPM is constant. You can also take the example of fan. Below the fan also vortex flow is created. So if the fan RPM is constant, what is the function of fan? It will absorb the electrical energy and it will convert the electrical energy into mechanical energy. So if the RPM is constant, so the conversion of electrical energy into mechanical energy is constant. So I can say total mechanical energy remains constant in the entire flow field. Okay, so now we are going to see V into R and V equal to R omega, how it is constant in the next page. Look at this here. So this is the very good explanation of the free vortex and force vortex relation between radius and velocity. So what you can see here, so if you take the free vortex flow and this is the center, right? So if you're away from the center, your velocity is low. That means I can write here, if you're away from the center, if radius is large, then your velocity will be less. If you're coming nearer to the center, your radius is small, but your velocity is large. Correct? That means the flow is adjusting in such a way that the product of V into R remains constant in case of free vortex flow. V into R remains constant in case of free vortex flow. Coming to force vortex flow, it is opposite. If you're going away from the center, then your velocity is more. That means if R is more, then your V is also large. If your R is decreased here, then your V is also less. Okay, so this is how it is related. So that is why we are having omega constant. Omega equal to V by R is constant, right? If one is increasing, another has to another also decreases, then only the ratio will be constant. Correct? So this is valid for the force vortex flow. Very good example. You can see with this is the center. From the center, if you're going away, like if the radius is increasing, your velocity also increasing. You can see the velocity also increasing. Okay. Let's see some of the examples of the force vortex and free vortex flow. The first one is showing the example of free vortex flow. You can see I told you about the natural words like whirlpool in a river. Whirlpool in a river. Some instances of a vortex include a ring of smoke, drag from the wing of an aircraft, a tornado, dust devil or water spot, hurricanes, sunspot on the sun, black holes, spiral galaxies. Correct? Some natural words will come into picture. So this is a good example of free vortex flow. Rotary flow observed in vast basin while draining the liquid through the outlet bottom. Here also, what is the natural force? Gravitational force. Gravitational force is the natural force. Gravitational force. Look at some example of the force vortex flow. Example of force vortex flow. You can see here the flow of liquid inside the impeller of a centrifugal pump and inside the runner of a hydraulic turbine. Correct. So impeller, pushes the liquid. So flow of liquid inside the impeller of a centrifugal pump. Centrifugal pump, we have to supply the power. Correct. Electrical energy we have to supply, or whether it is a hydraulic turbine also. So the turbine pushes the liquid actually. Turbine pushes the liquid. So this is a kind of force imparted to the fluid. So this is called as good example of the force vortex flow. Runner of the hydraulic turbine. Correct? Runner of the hydraulic turbine. So that's all about the free and force vortex flow. And we are going to see the numerical in the next section. Okay. Thank you.